Welcome, curious minds, to the Deep Dive. I'm Ethan Cole, your guide for today's exploration. And with me, as always, is our brilliant expert, Olivia Wells. Today, we're plunging into a field that's, well, it's absolutely vital for global safety and sustainability, geotechnical engineering, specifically how it relates to tailings management. We'll be drawing heavily from this really insightful academic paper focused on the impact of density and rainfall on tailing slope stability. Think of this as your essential shortcut, your way to understand the unseen forces that can make or break these massive structures. Our mission is to pull out the most critical insights from this complex research, helping you grasp what truly makes tailings facilities vulnerable and, what the science tells us about managing those risks. And just a quick note for those of you who want to dive even deeper into this crucial world, the Tailings Podcast, founded by Mohammed Sabi, is an excellent resource. It's a fantastic initiative really pushing for sharing vital knowledge and sparking innovation within the industry. His vision really shapes it. But right here, right now, we're focused on this specific deep dive.
Olivia, it's great to have you here to help us unpack this.
It's great to be here, Ethan. This topic, it has such profound real-world implications. I'm looking forward to connecting the scientific dots directly to, the safety of communities and environments for everyone listening.
Absolutely. So let's start at the beginning. For anyone who might not be familiar, what exactly are tailings, and why are they such a big deal globally?
Right. Tailings are essentially the leftovers, the waste products after you extract valuable minerals from ore. So picture a massive industrial process separating gold or copper from rock. What's left behind is this slurry, a mix of finely ground rock, water, and often some residual chemicals. And this waste, it's typically stored in these huge impoundments. We call them tailings storage facilities, or TSFs. Now, here's the really astonishing part, and frankly, it's alarming. The failure rate for TSFs is significantly higher than for other water dams. The paper we're looking at says it's more than 2 orders of magnitude higher.
2 orders of magnitude, so like 100 times more likely to fail. Wow.
Exactly, over 100 times. It's a stark comparison.
And we've seen some absolutely devastating examples recently, haven't we? The headlines have been pretty grim.
Indeed. The paper, it highlights several really notorious failures that sent shockwaves across the globe. You take the Mount Poly Dam collapse in Canada back in 2014. That one event released 24 million cubic meters of tailings.
24 million. It's hard to even picture that volume.
It's immense. Imagine 9,600 Olympic swimming pools filled with mining waste pouring into a pristine fishing lake.
Oh, wow.
Then there's the Fundão Dam failure in Brazil in 2015. That polluted an astonishing 668 kilometers of waterways, just decimated ecosystems and communities. And maybe the most tragic, Brumadinho, also in Brazil, in 2019, over 250 people killed.
Just awful.
And it released nearly 10 million cubic meters of waste. So these aren't just statistics, right? They're stark reminders of how important it is to understand, predict, and prevent these TSF failures.
So looking at these catastrophic events, it's clear there's something inherent in the material, or maybe how it's managed, that makes tailings so prone to instability. What does the science point to? What are the key culprits?
Well, the paper really zeroes in on 3 interconnected things: the soil's density, its saturation, how much water is in it, and crucially, the impact of external factors like rainfall. Tailings often have a high iron content. Now, that might initially help bond particles together, give it some strength, but that very structure can be weakened, sometimes critically, by things like intense rain or even internal changes in the water content. So this brings up the big question the researchers tackled. How do these factors interact? How do they influence the overall stability? And, what's the tipping point from stable to collapse?
Okay, so let's zoom in on density first. The paper talks a lot about dense versus loose slopes. What exactly is that distinction, and why is it so critical for predicting stability?
Right. This gets into the core physics of soil behavior. It's really interesting. Imagine building a sandcastle, right? If you pack the sand tightly with just the right amount of water, it stands firm. That's kind of like a dense slope. But if you try to build with very loose, dry sand, it just crumbles. That's your loose slope. Now, the study used these incredibly sophisticated tools. They're called centrifuge models.
Centrifuge models.
Yeah, they let you simulate real-world conditions like the huge gravitational forces on a dam, but at a much smaller scale in the lab. It's pretty clever. And what they found was a really dramatic difference in how these slopes fail. Dense slopes, they tended to fail slowly in a ductile way and progressively. Think of thick dough stretching before it breaks. They call this dilative behavior. The soil absolutely expands slightly as it deforms.
Okay, so it gives you some warning.
Exactly. It gives warning signs, maybe allows for intervention. But in stark contrast, the loose slopes, They experienced rapid, brittle, catastrophic failures, like a dried-out cookie just shattering without warning. This is contractive behavior. The soil compresses and loses its strength almost instantly.
Wow.
The implication is profound. The type of material can decide if a failure gives you a chance to escape or if it just explodes.
So fundamentally, looser material collapses much more suddenly. Less warning. That's terrifying from an emergency perspective.
Precisely. It's the difference between, say, a slow landslide you might see coming and a sudden, complete implosion. The paper also gets into the specifics of the materials they use, like icar sand and actual gold tailings. They measured things like specific gravity, how dense the particles are compared to water, the angle of shearing resistance, that's the internal friction resisting sliding, also effective cohesion, sort of the stickiness holding it together, and saturated permeability, which is how easily water flows through when it's totally soaked.
Okay, so those exact properties dictate how it behaves under stress.
Exactly. They define its inherent strength and its likely failure mode.
And how does water or saturation play into this density picture? You mentioned it's not just density alone. We're talking about water within the soil structure, right?
Absolutely. Water content and what we call pore water pressure are fundamental, absolutely critical. Think of soil as solid particles with tiny spaces or pores between them. These pores can hold air or water. Now, when water fills these pores and starts pushing outwards against the soil grains, that's positive pore pressure.
Okay.
It essentially reduces the friction between the grains, makes the soil weaker, almost like lubricating it from the inside. And the study found, unsurprisingly, that positive pore pressures significantly reduce stability. They make a slope much more likely to fail.
Right.
Conversely, you can have negative pore pressures, which we also call suction. This happens in unsaturated soil, where water is held tightly in the pores by capillary forces like water in a sponge. This suction actually pulls the soil grains together. It increases the strength.
Ah, I see. So less water, or rather water held under suction, can actually make it stronger.
Temporarily, yes. The researchers used these sensitive devices called tensiometers in their experiments. They're like tiny gauges measuring the suction. And here's something fascinating they found. Even slight differential settlements, tiny movements during the centrifuge spin-up, especially in the really loose slopes, could cause a localized reduction in those pressures, which means even subtle internal movements can immediately start contributing to instability by messing with that internal water balance.
Okay, so that's the water inside the tailings. But what about rainfall from the outside? That's a huge unpredictable factor, especially, with climate change and more extreme weather. How does a sudden downpour affect these structures?
Yeah, that's a critical question engineers constantly grapple with. How does a big rainstorm translate into immediate risk? So the study modeled a pretty severe rainfall event. 60 millimeters per hour for 30 minutes. That's a serious downpour.
Definitely.
They wanted to see its effect on the factor of safety, or FAS.
FS, right. That's the stability measure. Ratio of resisting forces to driving forces.
Exactly. An FOS of 1.0 means it's right on the verge of failure. Below 1.0, it's failing. Engineers always aim for something higher, like 1.3 to 1.5, for a safety buffer.
So, a higher FS is safer. Anything near 1.0 is precarious. What did the simulated rain do to those numbers?
Well, they found rainfall consistently and significantly reduce the factor of safety, especially in the loose slopes, as you'd kind of expect. For instance, in one loose slope model, the FOS dropped from 1.18 down to 1.1C.
Okay, that might seem small, 0.02, but you're saying when it's already that close to 1.0.
Exactly. When you're hovering just above 1.0, even a tiny drop can push you from precarious but stable into imminent collapse. It's like standing right on a cliff edge. One tiny nudge makes all the difference.
That really clarifies the significance. But then you mentioned an interesting anomaly. The very loose slope, test 3, its FOS dropped less dramatically, from 1.58 to 1.55. That seems backwards if looser is generally worse.
Right. It does seem counterintuitive at first, and this is where the real nuance comes in, the sort of double-edged sword aspect. The paper explains that in that particular very loose slope, there was initially very strong suction in the unsaturated soil. Remember, suction increases strength.
Ah, right. The sponge effect pulling things together.
Precisely. So that strong suction initially helped maintain a higher factor of safety, acting like a temporary protective shield against the rain. However, and this is the crucial bit if that suction gets lost, maybe due to prolonged heavy rain or an earthquake or changes in the water table.
And the stability could plummet.
Very rapidly and unexpectedly. So it highlights just how paramount the behavior of unsaturated soil is. Its ability to maintain that vital suction is critical for stability, and it really influences how rainfall impacts the slope. It's a complex dance.
That's fascinating. So that initial suction gives it a kind of deceptive strength. And here's another really intriguing point from the paper. It mentioned that ponded water collecting at the toe or bottom of the slope, could initially increase the factor of safety. That sounds completely wrong. Why would more water make it safer, even temporarily?
Yeah, it sounds paradoxical, doesn't it?
Yeah.
But it's about a specific mechanical effect called buttressing. Think of it like this. The weight and pressure of that ponded water at the toe can temporarily push back against the slope base. It essentially provides a bit of external support.
Like a prop holding it up.
Kind of, yeah. It increases the resisting forces, and so briefly, the FS might go up. And it's but this is almost always temporary, because what happens next?
The water soaks in.
Exactly. That ponded water inevitably infiltrates the soil at the toe, leading to saturation. And once that part of the slope gets fully saturated, those positive pore pressures start building up. And as we discussed, that significantly reduces the soil's strength and the overall stability.
Ah, I see. So a temporary, localized benefit quickly becomes a much bigger, more dangerous problem.
Precisely. It's a classic case of an immediate deceptive positive leading to a delayed, potentially catastrophic negative. Very important for monitoring.
Absolutely crucial. So with all these complex interactions, these dynamic behaviors, how do researchers double-check their findings? How do they make sure the centrifuge results are robust?
Great question. They use another powerful tool, sophisticated numerical modeling software. Think of it as creating a highly detailed digital twin of their physical centrifuge experiments. They input all the measured soil properties, the rainfall conditions, everything, into a powerful computer program.
So they run virtual simulations to see if they match the lab results.
Exactly.
Yeah.
And the numerical models largely confirmed what they saw in the centrifuges. Dense slopes in the models also showed that slow, ductile deformation, the warning signs, while the loose slopes, again mirroring the physical tests, showed those rapid, brittle, catastrophic failures. So, this convergence, getting similar results from both physical lab tests and advanced computer modeling, it really strengthens the reliability of their conclusions. It gives engineers much more confidence when they apply these findings to designing real-world TSFs.
That makes sense. Using both methods gives you more certainty.
And numerical models also let engineers explore a huge range of what-if scenarios, different rain patterns, different soil types, even earthquakes much faster and cheaper than physical tests. It helps optimize designs and do better risk assessments.
Okay, so we've gone really deep here. Density, water, suction, rainfall, modeling. What are the ultimate actionable takeaways? What should listeners really hold on to about TSF stability?
I think the core conclusion is this. The stability of these massive tailings facilities is profoundly influenced by the soil's starting state, its density, because that dictates how it responds to water pressure. Loose, contractive soils are just inherently far more susceptible to those rapid, brittle, catastrophic failures, especially when triggers like rainfall come into play. And while things like ponding water might offer a fleeting, localized buttressing effect, it inevitably leads to saturation and a dangerous reduction in stability down the line.
And maybe the single most critical insight for, the engineers and planners actually building and managing these things.
It has to be the behavior of unsaturated soil, understanding and crucially accurately modeling how tailings behave when they're not fully saturated. That's essential, especially under varying, unpredictable rainfall. Current engineering often leans heavily on saturated soil mechanics, but this research really underscores how vital unsaturated soil mechanics are for accurately predicting stability.
So ignoring that unsaturated phase is a major blind spot.
It can be, yes. It really demands more sophisticated monitoring, more nuanced design thinking, and a proactive approach to managing that delicate water balance within these huge structures.
Yeah. What an incredible deep dive. We've really unpacked the hidden complexities here, seeing how density and rainfall aren't just minor details, but fundamental drivers of stability, capable of turning a slow creep into a sudden catastrophe. The stakes are just immense.
Absolutely. And understanding these nuances, especially that critical role of unsaturated soil behavior, it isn't just academic theory. It's vital information for engineers, for policymakers, for communities living near these facilities. We need to develop more robust, safer solutions for managing mining waste. It's really about ensuring that terrible events like Fundão and Brumadinho aren't repeated.
Right.
Building structures that can withstand both internal pressures and the external forces of, well, a changing climate.
Absolutely. And the whole discussion really makes you think, doesn't it? If a tiny change in that factor of safety is so critical, what kind of advanced real-time monitoring can actually capture those subtle shifts in density and water content before a crisis hits? And how will climate change, with potentially more intense, unpredictable weather, further challenge how we understand and manage TSF safety? Definitely something for you to mull over. Until next time, keep digging deeper.